the earlier session, we have discussed on what is a Jacobian matrix and what is the importance of analyzing the Jacobian matrix. In this session, we will be discussing on how to derive the Jacobian matrix for RR manipulator. So we are going to derive the Jacobian by using formula method. So the Jacobian matrix, you can just divide it into the linear velocity components and the angular velocity components like this. So in this, the formula to derive the linear velocity component for a revolute joint and a prismatic joint is different. For revolute joint, the linear velocity components in the Jacobian matrix can be derived by using the formula Zi minus 1 into, this is the cross product, okay, cross product of Zi minus 1 and On minus Oi minus 1, and for prismatic joint it is Zi minus 1. The same way, the angular velocity components, if it is a revolute joint, that is obtained by using Zi minus 1, and if it is a prismatic joint, the angular velocity components are equal to 0. So to derive the Jacobian matrix, so we need to get the Z components and O, where this Z is obtained from the and O, they both are obtained from the transformation matrices. So here the example that we have taken is a 2R manipulator. So when we derived the forward kinematics of the 2R manipulator in our earlier sessions, we have already got this transformation matrices, that is the transformation matrix of the first frame relating to the reference frame and the transformation matrix of the second frame relative to the reference frame. So from this, so this is from T1 to 0. So this component, that is this is nothing but your Z1. And in the same way, in your transformation matrix T2 to 0, this will give you Z2. Okay. Likewise, here we also want O. So here that is the position. So this, I will take a different ink. So this is nothing but your O1, and this part of the transformation matrix, this is your O2. Right. So once you get the transformation matrices, you can get Z1 O1, likewise Z2 O2. So once you have got that, just substituting in this formula, you can get the Jacobian matrix. So here in the Jacobian matrix, it is a 2R manipulator. So you have two columns. One is J1 and J2. So J1 column you can just obtain by using the first transformation matrix T1 to 0. And the J2 column you can obtain by using the second and the transformation matrix, that is T2 to 0, right? So we have got all the required values to substitute in the formula. So let us see. So we have taken, so Z0 is always, so remember Z0, it is always assumed to be 0, 0, 1. Okay, 0, 0, 1. That is because the alignment of the 0th frame with respect to itself, right? So it is 0 degrees, so cos 0 it will be 1. So this will be 0, 0, 1 always, and already we have derived Z1 to be 0, 0, 1. And also this is a positional vector of the 0th frame related to that frame itself. So it should be 0, 0, 0, right? Because they both share the same origin, right? Then O1 to 0, which we have got from the transformation matrix T1 to 0, and O2 to 0, which we have got from the transformation matrix T2 to 0. So now we have got all the values. Yes. So now we have got the values that is required for substitution in the formula. That is, we have got Z0 that we have assumed as that is always, or it is not assumption, it is the fact that it is always 0, 0, 1, and O0 it is 0, 0, 0, that is the position of the zeroth time relative to itself. So the both the origins are same. So it would be 0, 0, 0. And O2 we have got it from the transformation matrix T to 0. And likewise Z1 we have got from the transformation matrix T1 to 0. And now O1 we have got it from the transformation matrix again T1 to 0. So O1 represents the positional vector of the transformation matrix T1 to 0. So whatever we require to be substituted in the formula we have got. So just substituting, we will be getting the J of Q as this, right? So now we have to take the cross product. So I'll just tell you how to take the cross product. So here it is a 3 cross 1 vector, and likewise here also it is a 3 cross 1 vector. So whatever we get should be also a 3 cross 1 vector. So which that is a vector with 3 rows in it. So the first row, how will you get it? So for that, just hide the first row of these two vectors. So you have to multiply 0 with the 0 and 1 with this element. So minus of, so 0 times 0, 0 minus 1 into this one. So you will be getting minus of R1 S1 plus R2 S12, right? And the same way, how to get the second element of the vector. So you have to hide the second row and you have to multiply 0 with 0 and 1 with 1. So this is the second row, already you have a minus. So here after multiplying 1 and this element, you have another minus. So it is minus of minus R1 C1 plus R2 C12, right? And to get the third element, so you have to hide this last row and you have to do a multiplication between these two, 0 with that element and the 0 with this, so which will be obviously 0 here. So this is how you get the first column. So what would be the first column? It would be minus R1 S1 minus R2 S12, and minus of minus, this would be plus. So you will be getting directly R1 C1 plus R2 C12 and 0. So these are the first three first three rows of J1. Okay, so you have two columns in the Jacobian, that is J1 and J2. So these are the first three rows of J1, and the next three it is be 0, 0, 1, 0, 0, 1, right? The same way you should also do it for the column J2, right? So this is the J of Q is equal to, so we have got J1, and now we have to also complete J2, so that is quite easy. So here just covering these first two rows, you have to multiply 0 with 0 minus R2 minus R2 S12, that would be the first element, and then the second element, you have to hide the second row. So it would be 0 into 0 minus of minus, so it will be plus, so it would be R2 C12, and the last row you will hide, so it will be getting a third row to be 0 and then followed by that 0, 0. So this was the Jacobian for the RR manipulator, right? So I have just written it separately here. So the Jacobian of two-link manipulator or RR configuration, it is J is equal to minus R1 S1 minus R2 S12, R1 C1 plus R2 C12 0, 0, 0, 1, and minus R2 S12 R2 C12 0, 0, 0.